All right. Yeah, honored to be kicking off the ComSec track here. First time in Phuket. HITB has been one of my favorite conferences for a long time, and so happy that it finally comes to Thailand. I've been living in Bangkok for a few years, so this is the first major conference that comes close, where I don't have to travel too far. My name is Karsten. I work mostly on critical infrastructure, telco networks, banks, stock exchanges, power utilities, whatnot. And today we'll talk about blockchain security. Now, blockchain is not a critical infrastructure, at least not yet. Some people believe it will become. It will replace the banking system and whatnot. Personally, I'm agnostic about the future of blockchain. It could become this world-changing thing, or it could just stay a really interesting technology. The reason myself and my team in Berlin are working on blockchain is not because it's already super critical for the world, but because it's super interesting as a technology, and it creates all of these hacking puzzles. And as a hacker, obviously, we love puzzles, and nobody more than these two geniuses, Louis and Gabriel, who are behind the research that led to today's presentation, right? Why we want to share this knowledge with you today is that we see that relatively few people, surprisingly few people from the security community are working on blockchain, despite all of these really, really interesting puzzles. And we observe that that's partly because of a misperceived threshold of entry. Many of you will think it's very difficult to start with blockchain hacking. Now, this presentation is going to change that. You'll walk out of here with an understanding of what kind of bugs you can find, and also with a tool chain to start finding them today. Okay, so no more excuses not to be fuzzing and hacking some blockchain systems after today. And that's very much needed because the world does continuously run into blockchain security issues. Now, as I said, I'm agnostic about the future upside about blockchain. It might change the world or might not, but it's very clear that there's a downside. People stealing money from blockchain systems and using them for criminal or even disastrous means, for instance, North Korea funding its nuclear weapons program. That's the part that we as a security community have an obligation to prevent, or at least make less. Right? And coming back to the puzzliness of blockchain, you'd be surprised to see how small security issues can lead to disastrous outcomes in blockchain systems, much unlike other systems where, for instance, crashes are not usually considered a big deal, or other small software issues. They can just be patched and go away. Let's look at an example here of a past bug. A single line. What is this? Probably an integer overflow. Yes, you see this multiplication here. So they're multiplying and they're calculating. In fact, this might not even be an overflow. Sorry, no, they're just multiplying things in an unintended way to basically calculate the number of tokens in a blockchain. So they can then divide by that number when it comes to voting, right? You always want to reach a majority, so you need to know how many tokens are. They're calculating this number too high, so they're dividing by a very, very large number, which means you can never win a vote. There isn't enough votes available to get to 50%, and because of this one line bug, in this case in the governance function, a blockchain that was at the time worth 65 million just disappeared. It couldn't govern itself anymore. A single small integer bug here led to the demise of this entire project, right? To our knowledge, this wasn't used maliciously. So this was really a self-destruct that nobody wanted to trigger. It was triggered, and the rest was history. However, somebody could have used this maliciously, of course. And the types of bugs we'll talk about today, they all fall into this category where a malicious actor could enrich themselves. Now, staying with this bug for a second. We see the destructive nature of this bug, but how could somebody make money out of destroying somebody else's blockchain? Well, keep in mind, blockchain systems are kind of financial instruments, and there's financial derivatives for them. So long story short, you can make money based on somebody else's bad luck, basically, by betting kind of in the stock market, by short selling, it's called, right? So you're taking out a bet that you say, this system is going to lose value. Somebody else is going to bet against you, and they say, this system is going to increase in value, right? So if you had this bug to destroy the system, that's how you make money, okay? So unlike in many other computer systems, here, a lot more bugs become relevant for criminals, because any bug that would show that the system is not as stable as people thought, that's going to allow you to make criminal money. Any bug that is slowing down the system or exhausting finite resources, that's going to drive down the price and make you money, right? So a very large class of bugs, including kind of random crashes, the whole fail-safe paradigm is put in question here, right? If everybody fail-safes, there is no system anymore, and again, the criminals make money, right? And this is in addition to the obvious way to making money in blockchain, but just stealing somebody else's tokens, right? So when we think about hacking a blockchain, you would think the way that criminals use this is there's some money in somebody's account, let's move that money around into somebody else's account, kind of a bank heist, right? But most of the bugs we'll be talking about today, they're more in the area of crashes, diminishing the viability of a blockchain project, and thereby cashing in on the short sell, right? Very important to keep that in mind. Now, there's a whole universe of blockchain-related security issues we're not going to talk about today. Any kind of financial scam or phishing attack, or let's say attacks on the Linux computers on which the blockchain system is run. All of this is also possible, but let's keep this out for today because you already know about these threats, right? We talk about just blockchain-specific hacking. And I'll go through this in 3 chapters. One, introducing the style of blockchain. Please join us. Yeah. That we're specifically talking about. Then introducing some nomenclature about what types of bugs we commonly find, and then give you examples about each of those bugs. I guess that's the part that you're waiting for. And then finally, we'll give you some tools and, in fact, a quick demo of the tools to really take away any excuses that you are not a blockchain hacker yet, right? At the end of this hour, you can and will be. All right. Sounds good? Yeah. So, we'll specifically talk about 3rd-generation blockchain. So a bit of history. So when you think blockchain, the first thing that you associate it with, of course, is Bitcoin, the 1st generation, which is surprisingly old already at this point, which was basically a virtual distributed equivalent to bank accounts. People had coins, bitcoins, so basically money in accounts, and you can move it around. So it was supposed to replace basically bank accounts and the banking system, but very single purpose. And because of its simplicity, there weren't many bugs found in that. It's still running today, and I guess we concluded that it's relatively secure from a cyber perspective. The 2nd generation then said, let's go beyond this idea of just bank accounts and moving money around, and let's allow actual contracts to live on the blockchain. So where we agree on some kind of financial contract that is then computed by the blockchain, and depending on how the trade goes out, automatically all the proceeds are distributed. Smart contracts. And of course you associate that with Ethereum. And Ethereum became so popular that people stopped believing in its viability. It's really this world-changing force, because so many people wanted to compute smart contracts on Ethereum that there just wasn't enough capacity. So there's a scalability issue. And Ethereum is one system that basically tries to meet the needs of anybody who ever wants to compute a smart contract. So it's a very generic system, and through that relatively slow, right? It tries to be everything for everyone. Now, the 3rd generation that's been popping up for the last 5-6 years, what we call 3rd generation blockchains, here you have custom-built blockchain systems, so that you don't have this one system to cater to the needs of absolutely everyone, but you have subject matter-specific projects, hundreds at this point, right? And most of them are built on just a handful of different technologies. So basically you have a base layer of technology, but you build your own blockchain from that. You attract users for your specific purpose, whatever that might be. And then in a perfect world, you're interfacing with some of these other specific purposes to create this global ecosystem. It's supposed to be very scalable, but just from me explaining it, you see how complex things are getting very, very quickly. And we'll be zooming in to a part of this ecosystem called Substrate. This is a programming framework that you can use to basically create your own blockchain relatively quickly, and then customize it to your application. And there's hundreds of projects built on this. And the ones that you might know are called Polkadot and Kusama, and then many, many others. And basically what Polkadot is a way of creating that underlying layer, basically the replacement for Ethereum, as well as the functionality that runs on top of it, which on Ethereum would have been smart contracts. And so these are basically these red and gray building blocks here. Now, blockchain systems are very complex distributed systems. There's many nodes running many pieces of software for communication, for computation. We'll be looking at just one of these components, which is the runtime. So basically, the blockchain nodes exchange messages, and then these messages are converted into the blocks, right? Hence blockchain, in the runtime. And it's there where we find all of the bugs that we'll cover in this presentation. So basically, simplistically speaking, as a blockchain project, you start with these red building blocks on the right-hand side. They're given to you by Substrate. You modify them and combine them in any way that you see fit for your specific application, and you have your own runtime that runs in every single node in your network. And then you build the actual functionality from these palettes. Again, libraries that are provided by Substrate. You add your own code. So you have custom code. You have standard libraries that you modified. You have basically an operating system underneath from standard components and stuff that you modified. So it gets really complicated very, very quickly. And that times several hundred projects that are running this, right? So as a security researcher, it's just a wall of complexity. And we want to help you now to kind of cut through that wall and to see the bugs behind it. Okay? So we have found well over 100 bugs in the blockchains that we analyze. We do this not just for fun, we also do this commercially. So we look at dozens of blockchain projects, and most of the bugs that we find, in fact, the vast majority, falls into these 5 categories. This is sorted by frequency. So on top of the list, those are the most commonly found bugs, and then kind of it diminishes as we go down. But yeah, expect the bugs that you will find in blockchains to fall into these categories. And we'll go into each of them in detail, just as a rough overview. The first category is a way of slowing down a blockchain or even completely stopping it. Often based on the blockchain kind of computing things wrongly and then kind of biting off more than it can chew, right? Again, we'll look into details there. The second type of bug is when you make the blockchain divert from its intended program flow. And this, of course, can lead to availability issues. And we already talked about, short selling and then getting rich that way. But this type of bug can also be used to really divert transaction in many cases. So basically move somebody else's tokens into your account, for instance, right? The third type of bug is to make the nodes crash, right? And again, you want to diminish kind of the viability of a blockchain. The fourth type is where you abuse some configuration settings, again, to make the kind of the logic trip up in the blockchain. And the final type of bug is again, making the blockchain choke on itself, but in this case, in more a permanent sense. So we'll go to examples as we go through this list. Any questions so far? I know I'm giving you a lot of information about an ecosystem that you might never have heard of, right? So if you do have questions, we're small enough group, just, let us know. All good so far? Okay, good. So then going through to the actual bugs, and I'll introduce each of those with kind of a rough scenario here, and then go through the actual bugs that make that scenario come to life. So in this case, the scenario is, again, somebody short sells a token because they have found an issue in the blockchain. So first they make sure that they can make money in the end. The criminals will. Then they're putting something on the blockchain that diminishes the viability of the blockchain. And then everyone looks at the chain and says, well, this doesn't work anymore. That's not worth anything. They start selling their tokens, and the original person gets rich, right? So what specifically are we exploiting in this first example? We're exploiting a wrongly set weight. So let me explain what this is. Basically, the cost of running an instruction on a blockchain. In these systems since Ethereum, and certainly in the third generation, a distributed network of computers runs other people's software, and they run it in kind of a the distributed ledger kind of way. So everyone needs to compute the same instruction and then agree about the outcome. So the time to run other people's instructions is always limited. For each block, there's only a certain compute time allocated. And so as the person who contributes code into that instruction, into that block, you have to pay for it. And different instructions take different amounts of time, so you have to pay different amounts. So there's a cost associated with every single line in your program. And those costs, called weight here, they're pre-computed for the blockchain system. So certain small instruction cost less and certain big instruction cost more. And whoever created the blockchain set those as static parameters. Now imagine our case where one of these is set wrong, much too low for what it should be. What you can do now is you can create a contribution to one of these blocks that takes a lot longer to compute than was benchmarked. In fact, it takes so long that you miss the time to generate the next block. So you're kind of choking on that instruction. You can't reach the next block, in which case basically the chain doesn't exist anymore, right? The next block is missing. And this type of bug is shockingly common, because it's relatively easy to prevent. It's the exercise that programmers need to go through is called benchmarking, basically looking at all of the different instructions and how long they take. As long as they get it roughly right, that's okay, right? You need to vastly underprice to make this a viable attack where somebody with relatively little resources can create a program that looks like it would compute quickly, but then takes a huge amount of time, at least much longer than one block computation, okay? So here we have a hacker who's willing to put some initial funds to get the tokens to even be allowed to run something on the blockchain, but then makes the blockchain choke, so their own tokens are basically worth nothing anymore, but so is everyone else's, and through this short selling, there's some criminal interest in that. Okay? So this is the simplest example, and possibly the most common in the systems that we look at, right? And completely avoidable again. So if you're programming blockchains, this should never happen. Let's look at perhaps a more interesting version of this, where you don't even have to put any initial investment. And this abuses a function. By the way, these are all real bugs that we found on real blockchains, right? So this existed at some point in reality. In this case, we're using the pseudo function. Just like in Linux, it's basically a function that makes everything run in super privileges. And almost nobody on the blockchain is allowed to call this, right? Only basically the governance function if you change major things on the blockchain. So basically, before program runs, it has to go through multiple checks. First, you check, for instance, the weight of the blockchain, right? Does this fit into our next block computation? And second, then you check the privileges. Is the person even allowed to run, for instance, sudo? In this particular case, you never reach the second check. You never check whether the person is allowed to run, because the way we put together these pseudo functions here leads to an exponential explosion in complexity. So basically, if you chain multiple of these pseudo calls, each one of them branches twice into ironically, in fact, kind of a security function. It computes the weight here, makes sure that you're not exceeding the weight. But because it calls this function twice in each iteration, you get this exponential explosion. And if you just chain together 41 of them, you're already at 1 trillion iterations. So just to check whether somebody is allowed to compute this, every node has to go through 1 trillion computations, which again makes it miss its next block computation. And again, the blockchain kind of chokes on itself, right? So the hacker is basically willing to crash the entire chain to enrich themselves, right? Good. Any question on this first kind of bug before we move on to even more complex, more interesting bugs? All good? Okay. So now we're getting into bugs that make the blockchain kind of divert from its intended program flow. And like I said earlier, this is good if you want to crash a blockchain, but also if you just want to move tokens around, kind of the bank heist style of enriching yourself. And in this case, let's say a competitor wants to show that this is not a good blockchain by way of diminishing its viability. Here we're looking at a simple integer overflow, right? You see how this keeps summing, and at some point, the number becomes larger than 32 bits, and it will wrap around, like integers do, right? So if as the criminal hacker here, you can supply any kind of number that would quickly sum up to something exceeding the 2 to the 32, you make this code kind of trip over. And in this case, again, somewhat ironically, we're abusing a security function again, where you have to provide a proof that what you computed as the weight for your function is actually correct. But this proof can be as complex as you want. And in this case, we make it look like it's very, very long, and it keeps summing until this explodes. So again, you make the node compute so long that it misses the time to compute the next block, at which case there is no chain anymore. Okay? So these types of bugs you'll find in all kinds of systems, but nowhere do they have the impact as on blockchain systems, right? And maybe as again, further going down the path of irony, let's say somebody wanted to fix this issue, and here they did. So, anyone familiar with Rust? By the way, Rust is the programming language that all of this is written in on Substrate. So, you have the normal functions like sum or add or subtract, then you have a checked version of it, which means there can't be any overflows, or in this case, underflows from the subtract. Right? So basically, if it were to underflow, it just stops the program. It says we're entering an undefined state here. So this is clearly a security function, or meant as one. But in this case, what happens if it just stops execution? Well, guess what? It's not going to compute the block. It's never going to reach that next link of the chain. So even if you prevent the underflow, unless you have some smart way of handling that situation that shouldn't never have occurred in the first place, you're again stuck on this blockchain computation. So it's really, the devil is in the detail here. You need a system that just continuously crunches out these blocks no matter what people throw at you. And turns out that's relatively difficult. Okay. Kind of still on the same branch of these bugs here, bugs that make the logic flow divert in unintended ways. This time, first bug I think of this kind, we're showing something that doesn't just crash a node, but gives you interesting hacking access. And we're using a function here that's used to validate identities. Think of like Twitter's blue check mark, right? Somebody's validating that, yes, you are crypto.com or whatever, right? And there's an authority doing that, in this case called the registrar. And the way this works on the blockchain is you put an identity out there for verification, including the proof that it's actually you, in one block. And the registrar picks it up. They say, okay, interesting. I'm being asked to verify something. I look at the proof and I send a message in one of the later blocks that in fact the identity that this person provided was correct. Okay? It's like a stamp of approval. Now, like I said earlier, these are highly complex distributed systems, so their behavior is somewhat unpredictable. And in this case, what the hacker tries to do is get another identity snuck in onto the blockchain before the stamp of approval is given, right? So the registrar is ready to stamp based on the earlier message. However, if you sneak in another message and different identity, it's going to stamp the wrong identity, so to speak, right? And how it can do this on the blockchain is by getting kind of prioritized computation. So we talked earlier about paying to run your code on other people's computer, and there's these wait functions, so there's a cost for each instruction. So that's the minimum you're supposed to pay. You can always pay more, tipping, right? You can always be generous and say, hey, why don't you just compute mine earlier, right? So with a little bit extra tip, the registrar never tips, right? With a little bit extra tip, you can sneak a message in that technically came later, but is put on the blockchain before. And it's so difficult to think through all of these corner cases, of course, right? But that's when you get, if you don't have any central authority anymore, but rather, distributed, everyone does everything kind of at their own time and maybe based on somebody else's tip, right? So really good example of kind of a logic diverting bug, that gets you really into trouble. Of course, at this point, the hacker can impersonate whomever and steal tokens that way, right? Okay, halfway done with the bugs. Any questions so far? Okay. Next, we're looking at more the classical crashing nodes. So this time not based on blockchain specific stuff necessarily, but really just making the program panic. It's called in Rust, right? So basically to exit from the current program flow. And like I said numerous times, in other types of systems, this is considered best practice. You want to fail safe rather than computing on a state that's kind of undefined and you know that something wrong happened, you rather stop. Or if you stop in a blockchain, again, the chain part of the blockchain stops being there, right? So in this case, again, kind of as a security precaution, they're unwrapping this to show that it's a legitimate value. Well, it's not, so it just stops, right? Yeah, pretty straightforward and relatively commonly found because, programmers from other domains just don't think about it, in this safety focused way, right? Okay. Now the final two classes of bugs, they're also, interested in diminishing the credibility of the chain. But not by straight out crashing it. These are more subtle ways of diminishing the chain. They're also more persistent. So a hacker with all of the bugs that we found so far might still be interested in these additional types of bugs just because it gives them a little bit more control over how much they impact the chain, so that maybe they don't want the chain to completely disappear. As long as the value goes down a little bit, they make some money, and then maybe they do it a little bit more, right? So there might be criminal interest in these more subtle bugs. And the first such category here evolves around kind of getting standard configuration settings wrong. And I'll give you one example. Here's one standard configuration that each of these substrate chains have. It's called existential deposit. So basically, it says how many tokens do you have to bring to be allowed as a participant of the blockchain? Because the tokens are supposed to be divisible, so you can split it and split it, split it, but you're not supposed to split it an infinite number of times and then have infinite number of people on the blockchain with very, very small amounts. So it should be a minimum amount that allows you to play, kind of the minimum deposit to open a bank account, right? However, of course, during the development, people often set this to 0 or very small value just so they can play with their own chains without having to get actual tokens involved. And then a lot of times they forget to set this to a sufficiently high value. So that means that somebody with a tiny amount of money can keep cutting this down and down and down and create new and new and new and new and new accounts, each time basically bloating up the chain and adding computation. And this kind of slows down and further down the entire chain. And the reason this is interesting is that you get to tweak the impact of your hack here, right? You get to choose how many times you do this. So kind of an elegant and trivial way to impact the viability of the blockchain. Also, unlike with the previous bugs, it's a little bit unclear how you would recover from this. So, I mean, in any event, any of these previous bugs will drive down the value of the chain and give you a short sale opportunity now. But then the maintainers might say, okay, we'll just create a software patch, everyone install the patch, and we'll try to build trust again. Here, with this bug, you have written basically into the history of the chain. You have created users, they have done transactions. How do you remove them from the chain through software patch, right? So you have a more subtle and longer term impact on the chain. Really devilish stuff here. And then let's look at one that takes this idea to the extreme. And we refer to these kinds of bugs as storage bloating. So again, you try to impact the chain in a way that is really difficult to recover from. And what better way to do that than just to fill up the actual chain memory with garbage or with whatever data. And again, that's the storage. And storage is a maybe somewhat unintuitive to people with terabytes of in their own computers, a very finite resource, because this storage, of course, is not just on one computer, it's on every computer that contributes to the blockchain, and forever. So it's not repurposable, right? So storage, let's say a gigabyte of storage in a system like Ethereum would cost millions of dollars to fill, literally millions of dollars, right? Because it's so scarce and forever storage, right? So we find some ways in other blockchains, again, completely based on software bugs, to fill storage a lot cheaper. Okay, $25,000 in this case for a gigabyte is not super cheap, but again, you get to change the market price of a tradable asset in significant ways. So people will exploit this when found, right? So, and like I said, the reason somebody would want to put up so much money to do this is the long-term persistency of the impact. Really, this is almost impossible to recover from. You'd have to really start from scratch if you wanted to forget about that part of the memory allocation or do some really heavy lifting in changing the blockchain. All right. These were all the bug classes. I know that was a lot. Some of these were found through manual review, but a lot of them were found through automated testing tools. And it's exactly those tools that I want to make you aware of, so you can start using them as well. With little to no understanding of the blockchain system, the tools will guide you to where you want to start reading up and seeing what is the impact here. And those 5 types of bugs that I've been talking about, they can generally be found through 3 different techniques, right? Some of these bugs, of course, with different techniques. We'll be focusing on that middle part, fuzzing, but just to quickly talk about the other ones. Static analysis is, in our belief, what the programmers of the blockchain should be doing. One example is this benchmarking to put the right cost for each instruction number. That's clearly responsibility of whoever creates the blockchain. But if you, like us, are doing security audits, and you have some suspicion that the programmer might not have done it or might have done it badly, of course, you want to do this as well, right? So there's good tools available. They're not difficult to use. It's just it needs to be done, right? That's the static analysis part. The manual review part, on the other end, that's really expert level, right? If you have years experience in source code audits, this would come naturally to you. But if you're just getting into that end blockchain, probably leave that for the future and focus on something where you can get started quicker, and that is fuzzing. Everyone familiar with fuzzing? Yeah? Yes? Maybe? No? So just as a quick summary, what is a fuzz testing tool? So it's basically an automated setup to keep feeding a program with different inputs and to try to do something interesting, like a crash, something unexpected. Okay. And kind of the art in creating a fuzzing setup is, what are you going to feed the program? Because if you keep feeding it the same thing, it will give you the same output. No point in that. So you need to introduce some kind of randomness, some way of permuting your inputs. And initially, fuzzers did really just do randomness. They would change bits or bytes in the code. But how are you going to, just by pure random chance, craft a legitimately looking, interesting messages for instance, this runtime to perceive as a blockchain transaction, right? There's almost no chance. So smart fuzzers these days, they take existing messages and they permute them in ways and then look at, do we hit new code paths? Do we trigger something else in the code that wasn't there before? Are we branching somewhat differently? And if so, then we found a meaningful message. Let's put that in a collection. And this collection grows, and each message in the collection we start permuting. So it's called coverage-guided fuzzing. So you want to hit every instruction in your code, at least with one of your messages. Then you're kind of done with your fuzzing. And then you start, plugging in different values, and you end up, for instance, putting very large values and then hitting some overflow, or you end up putting many instructions that by accident were put with a too little cost, and you're exceeding the runtime of a block. So it's almost magical to watch how a fuzzer, by basically guessing, finds all of these corner cases in a program. And of course, you have to guess millions of times, literally millions of times to get lucky a few times. But I mean, we're talking about computers, so you can run things millions of times, of course, in almost no time. We didn't create a new fuzzer. We're using existing fuzzers, two of them, AFL++ and HongFuzz. These are kind of best in class. But we created two things to make them work really well for blockchain. One is a way of using multiple fuzzers to work as one, to kind of share the knowledge and to contribute to the seed pool in a shared way. That's useful beyond blockchains, of course, right? So if you're fuzzing anywhere else, you use that tool that we're releasing. The other thing that we created is called a harness, specifically for Substrate. So a harness basically sets up a program in an interesting way, creates a few user accounts, maybe put some tokens on the blockchain, creates kind of real life circumstances to then start putting messages into it, right? And it's not that difficult to create a harness, but if you're just starting, you have no idea where to start, right? So use our harness, use our instrumentation for this fuzzer, and you can start pretty much right away. Which leads me over to the demo of our fuzzer. You want to see a demo? We actually pre-recorded this, the demo guides and all. So I'll hope that the AV setup works well. And in fact, while this is playing, it's about 8-9 minutes. I'll be on the side. So if you want to, if there was anything unclear, we're like, oh, no, I'm not ready for the demo yet. I have some simpler questions. Come find me on the side and we can talk about that separately. Okay? Yeah. Okay.
Hello, Phuket. So today I'll be showing you a demo of our Substrate runtime fuzzer. So let's say you're a security researcher and you want to analyze a project that you just found that's a Substrate-based blockchain, and it's the code is open source on GitHub, and you want to find bugs but you don't know where to start. Well, our fuzzer might be a good place for you to start poking around and see if maybe you find an easy low-hanging fruit to report. So this the demo that we'll be showing you today, it's actually based on the Node template, which is a template runtime that's included in the Substrate repository itself, and it only contains a handful of modules, as you can see here, and one of them being the template module, which we'll come back to later because that's where we'll insert our bug. So you've got your runtime directory here, and what you want to do is create a sub-project called Fuzz, and then include our fuzzing harness in there. and maybe do a bit of dependency management here to actually import all of the right stuff. Import our fuzzing tool, which is called Ziggy, and then you're basically good to go. So this harness is actually about 350 lines of code that's going to import stuff from all of the dependencies and from your runtime, and actually set up the runtime in a way that makes it interesting for the fuzzer to analyze. That means, for example, creating a couple of accounts and giving them some base balance, and then the fuzzer is going to be able to access those accounts to actually send out the transactions for fuzzing. Because if you just didn't do that, then probably the fuzzer wouldn't be able to find anything, because the fuzzer wouldn't be able to call any method, any dispatchable method whatsoever. So let's say you've set everything up like this. Next step, what you need to do is get a server and then actually launch the fuzzer. So here I launched Ziggy on a couple of cores just a few minutes ago. It hasn't found anything yet, but potentially in the next few minutes it might find the crash that we're looking for. Now, what crash is that? This is a crash that we inserted into the node, the palette, the template palette. So this template palette, it contains two dispatchable functions. The first one is called do something. This do something function takes as an argument a U32, an unsigned integer of 32 bits, and this something value is put into the storage, meaning it's basically inserted into the database at a specific spot. If you call that method again, it's going to reinsert at the same spot another integer. And there's a second dispatchable method called cause error, and this does not take an integer as an argument. What it does is that it's gonna get the value from the storage, and then if there's nothing, it just returns an error, no harm done. If there is a value, then what it's gonna do is that this is the original code. It's gonna add one in a checked manner to the old value, and then if the value has overflowed, it's going to return this storage overflow error, which is a nice way to handle these overflows. It's a sane way to handle overflows. And if the value did not overflow, if the addition did not overflow, then it's just going to set this new value, so old plus 1, into storage. Now we've replaced that with this new is equal to old plus 1. This is because an integer overflow is they're very common in the Substrate ecosystem. It's something we see every week, and they're quite easy to find by the fuzzer. Now, why are they easy to find by the fuzzer? In a normal blockchain environment, the binaries, the runtimes themselves, they're compiled in release mode, meaning that additions and multiplications and subtractions, they can overflow, and the binary, the code itself won't mind. Meaning that, this U32 U32 max plus 1, it's gonna overflow, it's gonna come back to 0, and then it's just gonna put that 0 into the value. It's not gonna do anything, but what can happen is that in edge cases, maybe the developers did not know or did not notice this overflow capacity, and this might lead to critical bugs in the blockchain logic itself. So imagine you are able to trigger some kind of an underflow in a balance exchange, then maybe you're able to steal more money, to get more money from another entity than you were supposed to, or get more money from them, or maybe set your balance to some kind of maximum possible value. This would be very bad. What the fuzzer does is that it compiles the binaries with overflow checks enabled, which is the behavior you have in debug mode in Rust by default. So it's gonna compile the binaries, but every time there is an addition, a subtraction, any kind of arithmetic operation, it's gonna add a check over it, and if the value overflows or underflows, it's gonna panic. and this allows us to find these bugs with with the fuzzer itself. Now, coming back to the fuzzer, let's see if it has found anything. Yes, crashes have been found. That's cool. So in theory, if you redo this same experiment, the fuzzer will probably find from a completely blank corpus, it's going to probably find the crash in about 20 to 30 minutes, which is quite cool. Now Ziggy is our fuzzer management tool, and it's going to launch a couple of fuzzers in parallel. So the first one is AFL++, which is the gold standard of coverage guided fuzzers. And it's going to launch a couple of instances in parallel of AFL++. It's also going to use HomeFuzz, which is the silver standard. Maybe it's one of the best fuzzers out there. And hopefully HomeFuzz and AFL++ are going to be able to learn from each other because they share they share their corpus in between themselves. And now let's see, cargo Ziggy run, with input, we are going to go into our crashes directory, and these are the crashes that we were able to generate, during this run. And this is a typical, Rust crash that we're seeing here. And if we try to see a bit more in detail what happens here, so here we see that it's running this file that was generated by AFL++. Then we go into block 1 after initialization. The first call is gonna be to do something with a value of something that looks a lot like U32 max. And this is basically our crash condition, right? You need to do something with value U32 max and then cause error, and in theory that should overflow. And what do we see? Next call, cause error, of course. And thread main panicked at attempt to add with overflow. So yeah, we found exactly the crash we were looking for. If we see here, it tells us to look into the palette template librs line 101, which is exactly where we would expect the fuzzer to crash. And then we have the whole trace of that to get up the chain in, just in case, maybe it was in a sub call of a sub call, and you can find your way back to the exact source of the crash by looking at these logs. All right, cool. You found your first crash in a substrate-based runtime. And everything that we showed you here is open source, including the harness itself, and the runtime here is the Nohl template runtime. That's a good practice target. And Ziggy, our fuzzing tool, it's a fuzzing manager, and is also available open source in the SRLabs team on GitHub. All right, now back to Karsten.
Yeah, very good. Very good. So, I hope that was accessible enough for at least the programmers and other, fuzzing experienced folks among you to say, I can start on this right away. But really, you wouldn't have introduced a bug, right? That was obviously what we did. You would just pull somebody else's source code from any kind of, blockchain repository, and they almost all develop open source. So even before a chain gets released, the code is already public, right? So you pull any of those repositories, you pull our two tools, you put them together, you find these kinds of crashes, if there are bugs in the chain, right? So you can go through, let's say, one or two chains per week even doing this.
Hello.
So, just in terms of where you would find them, there's these two tools, both of them on the SRLabs GitHub. The harness itself, and the Ziggy tool to instrument the other fuzzers, right? Please try this and let us know how it goes, your experience, right? I mean, we developed this for the community. That's you, so any feedback is appreciated. In terms of what you will find, we find between 2 to 3 bugs on average per blockchain project we analyze. And like I said earlier, it's kind of in in descending order, roughly in these 5 categories, right? So if you pick a random blockchain project that hasn't gone through a security audit, do expect to find 2 to 3 bugs between fuzz testing and some manual analysis, of course. So with the fuzzer itself, maybe let's call it 1 to 2 bugs on average, right? So it won't take a long time for you to find stuff yourself. And yeah, like I said, this is for you. So let us know how it goes, and would love to hear some questions now. In fact, Louis, whom you saw in the video, he's dialed in now through Teams as well. So ask us any questions that are relevant for you to get started, or anything you didn't understand in what we discussed. And don't be shy.
Any questions?
Hello. So my question is regarding the 5th bug class,
Sure.
storage bloating. So I'm not too familiar with like blockchains, but I remember reading that when you are interacting with like a smart contract and you are performing like a storage operation, you will need to sort of pay transaction fees for that transaction, and that will depend on the amount of storage that you are going to be writing onto the chain. So does that mean that bug would allow you to essentially store more data than what it would cost you, like based on the gas fees?
That's a good question. I'll give you the simple answer, and then Louis will tell me where all I went wrong. So my understanding is that this particular bug, you're not actually calling something that reserves storage for you. You're calling a function that, as a kind of an externality, as a side effect, also writes something to the chain. But really, you're registering a bridge here, which is, in a sense, underpriced because it also puts something on the storage, but it's not to your benefit. It's kind of like bookkeeping stuff, right? And that's how you can use this extremely cheap call to cause something that would otherwise cost a lot of money. But yeah, Louis, fill in all the details that I missed.
Can you hear me?
Yeah.
Perfect. Yeah. I mean, what Karsten said was overall right. I would just add that adding an item to the storage will be benchmarked as, like, the time that it takes to write to the storage will be included in the cost. So you will have to pay that, but then there is no extra cost for the fact that you did a storage operation, and that's up to the developer to actually add some kind of a deposit for long-term storage that is then potentially reimbursed when the item is removed from storage. Yeah, and this is mainly to be used for large item storage, and this example of a bug was a large item storage that was put into the database.
Oh, so you are not actually storing anything like permanently?
No, the goal here is to waste storage for other people. Again, the whole blockchain world is a little bit weird in that if you just make somebody else's life harder, you can make money, right?
Okay. Thank you.
Any other questions?
All right. Well,
okay.
Thank you,
Karsten.
Yeah, no, thank you. And obviously, if other questions arise, yeah, thank you. If other questions arise, or you were just too shy to ask them, find us on any of the medias. I guess for me, more LinkedIn. For the other two gentlemen, more. What is that Twitter thing now? The Security Exchange, yeah. Or just hit me up when I'm in Bangkok. Kung Tep Mana Kon for coffee, right? Any questions on security, careers, or anything, right? I'm here for you. Yeah. Well, thanks again. And thank you, Louis, for getting up so early in Berlin. Yeah. Bye now.